All right, welcome. Today's lecture is on rolling motion. Specifically, I wanted to talk about rolling without slipping. So let's imagine a uniform cylinder of radius r that rolls without slipping. And so when I say rolls without slipping, what I mean is that it's not sliding across the floor. Instead, so this point here is in contact with one point on the floor and won't be in contact with the floor again until this thing has rotated a full 360 degrees. So, um, so I've sketched a little arc segment of angle theta, and this little segment of the circumference s will equal r times theta, right? If you allow theta to be 2 pi radians, then that little arc takes on a value of 2 pi r, which is the entire circumference, right? And so if we allow this thing to rotate through some angle theta and it rolls without slipping, then uh, I've tried to sketch kind of the unwound bit of arc on the ground, right? Such that this point will move to here, and this point will be on the ground, right? So as it rolls from this position to this position without slipping, each and every point along that arc is in contact with one point on the ground. That's what I mean by rolling without slipping. And we could say that the center of mass speed is just ds dt, which will be r times d theta dt, right? Because s is r theta. So if s is r theta, ds dt is just r d theta dt because r is constant. But d theta dt, remember, is how we described the angular speed omega. And so the center of mass speed, VCM, is just equal to r times omega. So hopefully this is okay. We could also describe the center of mass acceleration as d dt of the center of mass speed, but we just said that the center of mass speed is r omega, and so the center of mass acceleration should just be r times d omega dt, but d omega dt we have previously described as alpha. And so we could say that the center of mass acceleration is just r alpha. We also, last week, derived this parallel axis theorem. And so um, the moment of inertia about this point is just the moment of inertia about the center of mass plus m times r squared, where r is the distance between the center of mass axis and this point on the ground axis. We also have that the kinetic energy is half times I about that point times omega squared. And so I can replace I about that point with ICM plus MR squared. And so I can say that the kinetic energy, half IP omega squared, is half times the quantity ICM plus MR squared times omega squared. We could multiply through and get half ICM omega squared plus half mr squared omega squared, which is half ICM omega squared plus, well, we already said that VCM was R omega, and so half mr squared omega squared is half m VCM squared. But note that this is just the translational kinetic energy. And so what this is telling us is that the total kinetic energy here for this rolling without slipping case is our half ICM omega squared plus half m VCM omega squared. And that's a useful formula that we'll come back to again and again. So let's look at I, a cylinder or a sphere, mass m, radius r. It's originally at some center of mass height h above the floor. There's some ramp path x, and the ramp is tilted some angle theta. And so we could say that the kinetic energy is half I center of mass times VCM over r squared, right? That's just omega VCM over r, right? Because previously we've said that VCM is r times omega. So omega is just VCM divided by r. Excuse me. So the kinetic energy is to be half ICM times quantity VCM over r and quantity squared plus half m VCM squared. Note that there is a half and a VCM squared in both of these terms, and so I can factor to say that the kinetic energy is half times the quantity ICM over r squared plus m and quantity times VCM squared, right? Convince yourself that you can go from this line to this line. If we're in a state where we can assume that mechanical energy is preserved, then we have that we'd have that the later kinetic energy plus the later potential energy needs to equal the earlier kinetic energy plus the earlier potential energy. And so the later kinetic energy, well, we already said that kinetic energy can be thought of thusly. So the later kinetic energy is just going to be this, where VCM is the later value of the center of mass speed, plus 0, because we'll set the 0 point of potential energy here at the floor. And then the earlier values, well, at the beginning, if we release this thing from rest, it has no kinetic energy because VCM is 0, started at rest. But it is some height h above above our floor. And really I should be a little more careful here and set it like so that the center of mass will be at the 0 point, right? So what we have here is that later kinetic energy plus later potential energy is earlier kinetic energy plus earlier potential energy. And so it has no potential energy when it's at the floor, so that term goes to zero, but it does have kinetic energy. At the beginning, if it was released from rest, it had no kinetic energy, but it did have mgh of potential energy. And so we can solve this for VCM, right? And so I'll leave this as an exercise for you that you can solve this for the center of mass speed at the bottom, multiply across by 2, and you get I 2mgh, divide by quantity ICM over r squared plus m and quantity, and then square root, and then divide top and bottom of the numerator and the denominator by m, and you'll get to this. So convince yourself that you can go from here to here. And I'd pause the video and make sure you can do that. So in this rolling without slipping I rolling downhill, released from rest, this is going to be VCM as after it is rolled down some height h. Recall previously that for constant values of alpha, we had that omega L is equal to omega E plus alpha delta T. We had theta L is equal to theta E plus omega E delta T plus half alpha delta T squared. We had omega L squared is equal to omega E squared plus 2 alpha times the quantity theta L minus theta E end quantity. And then we also had theta L is equal to theta E plus half times the quantity omega E plus omega L end quantity delta T. Note that we also had similar equations in our 1D kinematic for constant acceleration. We also have this thing that looks a lot like Newton's second law, right? In fact, we have seen previously where this comes from, but which is Newton's second law. But we can say that the sum of the torques is equal to the moment of inertia times the angular acceleration. We could describe the rotational kinetic energy as half I omega squared. We could describe the angular momentum as r cross p. We also have this other way of describing Newton's second law, that the sum of the torques is, or at least Newton's second law for rotation, is that the sum of the torques is equal to the first time derivative of the angular momentum. And so we can take these statements, right, and let's see. Oh, I didn't actually include it. This is a statement from our last lecture then, that the sum of the torques is r cross f, and that this statement, that the sum of the torques is dl dt, and so that tells me if the sum of the torques is equal to both of these things, they must equal each other, that r cross f has to equal dl dt. But if L is equal to r cross p, then dl dt, we could write as r cross dp dt plus dr dt cross p. And assuming that r isn't changing, then dr dt is 0, and so this second term goes away. And so we can say that the sum of the torques is just d r cross p dt. Hopefully that's not terrible. If we allow our rolling object to rotate about the z-axis, we could say that v of some incremental little bit of mass V sub I is just equal to Ri omega I. And we could say that the angular momentum then is just mi Ri Vi. Um, and so we could say that L is mi Ri squared omega, right? So since omega itself, since V itself is R omega, L, which is MRV, is just going to be MR times R omega is MR squared omega. Uh, the LZ is just the sum of all of the incremental little bits of angular momentum, is the sum of our MR squared omegas. If they all have the same angular speed, though, then I can bring that out of the summation and say that this is equal to the sum of mi Ri squared times omega. But the sum of all the mi Ri squareds is just what we've been calling the moment of inertia I. And so we can say that Lz is just equal to I omega. And so lastly for today, then dLz dt, right, would just be I times d omega dt, but d omega dt is alpha. And so we can say that the first time derivative of the angular momentum is I omega, which is at least justification of this statement. So I rushed through that a little bit, but that is our lecture for today. Hopefully this uh, isn't too terrible. In our next lecture, we'll do some examples and we'll kind of round out our discussion of this. You have lab tomorrow. As always, you guys are awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your day, but not so much that I don't see you tomorrow.